Okay, so we're going to consider 2-point charges here, each separated by a distance d. So if we draw our coordinate system here, and then we want our charges to be at some distance d over 2, because the total distance is d. And then we want to know what's the electric field up here at some distance z above the z-axis. Okay, well, we know that the electric field at this point due to this charge is just 1 over 4 pi epsilon naught. So the electric field due to the first charge is 1 over 4 pi epsilon naught times the charge q divided by the distance it is from itself squared. Okay, that's it. And this is in the r hat direction, so that would be pointed off in that direction. Then the second electric field from the other charge is 1 over 4 pi epsilon naught q over r squared, r hat again in their own its own r hat. And then we know that the total electric field is just E1 plus E2, okay, added together, and that means the x components should cancel each other out, so you're only left with the y component. So then we have 2q over 4 pi epsilon naught times r squared times the cosine of theta. Okay, and so I could leave it in those terms if I want to. That would be good enough, where this is the angle theta here, because it's equal to this angle theta over there. And we could replace this theta even if we just want to put everything in terms of the origin. We could set this equal to 2q over 4 pi epsilon naught, and then r squared. What is r? This distance r is just the square root of z squared plus d over 2 squared. So r squared is z squared plus d over 2 squared. And then we've got 2 of those, and then we've got a cosine of theta. Cosine of theta adjacent is z, so we'd have z over the hypotenuse, which is the square root of z squared plus d squared. So we end up with 2qz over 4 pi epsilon naught times z squared plus d over 2 squared, not to the squared, but to the 3/2 power, because we have z squared plus d over 2 squared times the square root of z squared plus d over 2 squared. So it's 2 over 2 plus 1/2, which is 3/2. And that's the electric field generated by those 2-point charges. Okay, so now let's consider a line charge here. And we want to show that the electric field above this is this form. So we're going to pick this little point here as our little charge bit, and that's a distance r. And this is a distance r. So let's call this r prime and that one r. And then we know that the separation vector is r minus r prime. Okay, and that's going to be the difference between this vector minus that vector, and it should give us that script r vector. Okay, and then we know that r, little r, this r here, this pointing vector to that point, is z, the length of this vector, times z hat, and then r prime is equal to the length here, x, to that point, dx. Okay, x to that, not dx, x hat. Okay, and so then we can rewrite script r in terms of this z hat minus x hat. So that is how you can rewrite what this separation vector is, because what we want to do is write this r in terms of our 2x and z coordinates, because as we sweep and integrate the electric field as we go through, we want to be able to have those things. Okay, so then if that's r, then the magnitude of r, or however long r, the script r is just a function of this. It's z squared, square root of whatever our x squared is plus whatever our z squared is. And then the direction, the little unit vector pointing this way, is by definition r hat, and that's just the vector itself, the script r vector divided by the magnitude of the vector. Okay, and that just normalizes it to be a unit vector, okay? And so that's going to be our r vector is z hat minus x hat divided by square root of x squared plus z squared. Okay, so what did I do? I know that script r is equal to this r minus that r, those two vectors. And I rewrite what those two r vectors are. The first one is some length z in the z-axis, and the other one is some length x in the x-axis. So then I can rewrite this r vector in terms of x and z components. Okay, so then the definition of the electric field, E, is just equal to 1 over 4 pi epsilon naught times the integral, and we're going to integrate from minus L to L, for example, minus L to L. And then we've got our charge, lambda over z squared plus x squared, and we're going to multiply that by our z hat minus x hat divided by, so this is our r hat vector. This is just charge over r squared, and then times our unit vector z squared plus x squared. Okay, so that's just q over r squared, and then dx. Okay, oops, dx. Okay, and if you do that, then you get the integral. Lambda is a constant, lambda over 4 pi epsilon naught, and then if you multiply these two things out, you get a z hat direction times the integral minus L to L, 1 over z squared plus x squared to the 3 halves dx minus x hat times the integral minus L to L of x over z squared plus x squared to the 3 halves dx. Okay, and that's your integral there. And if you do a couple more simplifying steps, then you get down to the result here. Okay, so then what happens is this so we have 1 over 4 pi epsilon naught times 2 lambda L over the square root z times z squared plus L squared. Okay, what happens when z is much bigger than L? That means z dominates in this term. Okay, so then this approaches 1 over z times the square root of z squared, because adding L squared to that does nothing. So that approaches 1 over z times z, which is 1 over z squared, which is approximately a point charge. When when L approaches infinity, and as L gets bigger and bigger and bigger, then you have L divided by z times the square root of L squared, which approaches L over z times L, which approaches 1 over z. So that's your difference, which is an infinite charge. Line charge is just 1 over r, whereas a short distance goes like 1 over r squared. Okay, so then we go on to the next thing, and given this electric field with these things, which I plotted on Math 3D there, what is the flux to the surface defined by y equals 3? So this is y. I know you couldn't do that on the exam, but there's our y equals 3, and we want to go to x equals 3 and z equals 3. Okay, and that is our surface. Okay, and we want to know what's the electric flux through that surface. Well, that's defined to be the integral of the electric field dotted into the area element. Okay, so this is the integral of 6xi hat plus 4y squared j hat, okay, dotted into dA. Now, what's our area? Well, let's imagine a little area element here. So that's in the x and the z direction, so we're going to multiply that by dx dz. But then when you have a dA vector, the result of the dA vector is always normal to the surface. So if we have dx and dz here, then the result of that is going to be in the y direction. So we got to put a j hat on our dA vector because it has a magnitude dx times dz, but it's pointing in the j hat direction. Okay, because that's what we want to do. We want to say take this area and then how much of the flux is going in the j direction, because that's what flux is. Okay, so we're going to integrate. Then we've got 6x I hat plus 4y squared j hat, okay? And if we dot that into j hat, we just have left over after all that. We just have the integral of 4y squared j hat dx dz, okay? And because the j dotted into I hat, so I hat dotted into j hat is 0, and j hat dotted into j hat is 1. So only the y component of this vector through the y direction is what counts. So we're going to integrate 4y squared dx dz. So we're going to have, and y equals 3 this whole time, so we can pull that out because that's a constant. So we have 4 times 3 squared, and then we have the integral from 0 to 3 dx times the integral from 0 to 3 dz, and this just gives you 4 times 3 squared times 3 times 3. And so that's 3 times 3 is 9, times 4 is 36. So we have 36 times 3, which is 324. Okay, and so that's the result of that integral. What is del dot E? Okay, del dot E is, by definition, if we go to the equations at the end, del dot, went too far. Del dot E is, did I go too far? Well, del is x hat d dx. So we're going to do x hat d dx ex plus y hat d dy y hat. Okay, and so this gives you d dx is, sorry, cat. Okay, so let me, my cat's locking on me. Oh, there he goes. Okay, so let's start over. So let's go back to del dot E. Okay, del dot E is, okay, here. Del dot E is 1 over epsilon naught rho. Okay, and so we can do that one, which we're going to do that in a little bit. But del dot E is, so this is del, and then we're going to take that and dot it into our E vector. Okay, so let's go back up there. And so we're going to have x hat d dx, and then times, let's just write it all out, 6x x hat plus 4y squared y hat plus y hat d dy, 6x x hat plus 4y squared y hat, okay? So then this x hat and that x hat gives you 1, so you have d dx 6x, and then this x hat times that y hat gives you 0, and then plus y hat dotted into x hat is 0, and y hat dotted into y hat is 1, so you have d dy 4y squared. So then this becomes derivative of 6x is 6 plus 4y squared is 8y. Okay, and so that's what del dot E is. And then what is the charge density? Well, we know that the charge density del dot E is equal to rho over epsilon naught. So we have our del dot E is equal to 6 plus 8y, and then we can evaluate that when x equals 1, y equals 2, and z equals 2. And so that is going to give us 6 plus 8 times 2, which is 22 epsilon naught. Okay, and so that's going to be the charge density at that point in space. And then we want to do the integral of E dot dl from 0, 0, 0 to 2, 2, 2. So we're going to take the integral of E, which is 6x x hat plus 4y squared y hat. We're going to dot it into a line element. Okay, this is where I saw a lot of mistakes. We're going to dot it into dx x hat plus dy y hat plus dz z hat. Okay, that's a line element because we're going to add these paths up. If we multiply, you get meters squared or meters cubed. So I saw a lot of dx, dy, dz. That's a volume, that's an area, and that's just one direction. Okay, so we're going to do the integral of, and then when we multiply this dot product through, we just get 6x dx plus the integral of 4y squared dy, because if I just do this explicitly, just to make sure everybody sees, we have 6x x hat times dx x hat, okay, and then plus 6x x hat times dy y hat. If I multiply this through to everything, right, then the x hats, you get integral of 6x dx here, plus, and then this is 0 because x hat dotted into y hat, since they're perpendicular, the cosine is 90, you get 0 from each of those things, okay? So our total integral then is just integral of 6x dx from 0 to 2, plus the integral from 0 to 2 of 4y squared dy, okay? And this is equal to 6x squared over 2, evaluated from 0 to 2, plus 4y cubed over 3 times the integral from 0 to 2. Okay, and then what do you get? 12 here. 2 times 2 is 4 over 2 is 2, so you get 12 plus 8 times 4 is 32 over 3, something like that. Okay, number 3, question is, consider this potential, what is E? So we know that E is equal to minus del V, and this is going to be equal to minus D, and I'll just put a minus sign here, D dx of V plus, and then x hat, plus D V dy y hat, and of course Z as well, but there's no Z component, so this is going to be minus, and then we get 2xy in the x hat direction, plus x squared plus 1 in the y hat direction, because dx squared y plus y dy is equal to x squared plus 1. Okay, and so that's our electric field, is given by this 2xy in the x hat direction plus x squared plus 1 in the y hat direction. Now we want to compute the line integral. Okay, so we're going to do integral E dot dl. Same thing, we're going to do the integral of 2xy x hat plus x squared plus 1 y hat. Okay, and then we have to dot that into our dx x hat plus dy y hat. No z hat again. Okay, so now we have an integral of 2x y dx, and the x dots into each other and the y's don't. So that's our first one, plus another integral of x squared plus 1 dy. Okay, and then we're integrating from 0 to 2 along the x direction. 0 to 2, where and y is 0 during that time. So this whole integral is 0, and then we integrate from 0 to 2 in the y direction, but we're at x equals 2 at that point. So that this becomes the integral of 0 to 2 of 2 times 2 is 4 plus 1 is 5 dy. So that's 10. Okay, and that's the answer you get here. And then if we plug in this one, our potential is given by x squared y plus y, and we want to know what it's at 2, 2, 2. So that's going to be 2 times 2 is 4 times 2 plus 2 is 4 times 2 is 8 plus 2 is 10. And then you see that, okay, because, so that's the v at 2, 2, 2. V at 0, 0, 0 is 0. If you put zeros in for everything, you get zeros coming out. So those two should be equal to each other. All right, and then sketch the vector at that point at 2, 2, 2. So we have our electric field is minus 2xy x hat plus x squared plus 1 y hat, and this is going to be minus actually. So then we have at 2, 2, 2, we have minus 2 times 2 times 2 in the x hat direction minus x squared plus 1. 2 times 2 is 4 plus 1 is 5 in the y hat direction. So we have minus 8x hat minus 5y hat. So if we, and this is at the point z plus, well, this is at the point z equals 2. So if I draw this coordinate system, then we want to go to the point x equals 2. So x equals 2, y equals 2, z equals 2. So at that point, the if this is x, y, and z, then our vector has the minus 8x component. So let me draw this a little better. Okay, so let's say that's minus 8 and then minus 5. And so if I put those two vectors together, head to tail, then there is our electric field vector is pointing in that direction. Okay. Next one, problem 4, consider a thin-walled sphere. It's got a charge on it, and inside the electric field is given by that. So the question is, what's the charge density in the sphere? Well, we know that according to one of the rules in Gauss's law, del dot E is equal to the charge enclosed divided by epsilon 0. So if we want to, if the electric field inside the sphere is given by this, then we can just do del dot E to figure out the charge inside. And if we go to our handy thing in spherical coordinates, then the divergence, del dot V, is 1 over r squared ddr, r squared times the r component. And we only have an r component, which was, you're welcome. So we're going to have 1 over r squared r squared times our r hat component, which is r sine theta. Okay, so this is going to become 1 over r squared ddr of r cubed sine theta. And this becomes 1 over r squared times, and the derivative of that is 3r squared sine theta. R squares cancel, and you just have that del dot E is equal to 3 sine theta. So then rho over epsilon naught, yeah, stop it. Oh no, I'm frozen. Oh no, I'm frozen, I broke it. Come back. Okay, there we go. 3 sine theta. Okay, so that's what del dot E is equal to. So then rho is equal to 3 sine theta times epsilon naught. Okay, so we'd have that. So rho would be the top bit. And if we want rho by itself, it's 3 sine theta epsilon naught. Okay. And then next question is, what's the surface charge of the sphere? So then we're going to do the full integral from 0 to r, and then integral of 0 to 2 pi, and integral of 0 to pi of our charge density, 3 sine theta epsilon naught, times our volume elemental, which is going to be r squared sine squared theta dr d theta d phi. And so we have the pull out all our constants. So we're going to have 3 epsilon 0 times the integral of r squared dr from 0 to r times the integral of sine of theta 0 to pi d theta times the integral of d phi from 0 to 2 pi. Okay, and then that gives us 3 epsilon 0 r cubed over 3 times, and then from the last integral from our phi thing we have 2 pi times the integral from 0 to pi of sine, oopsies, sine, this should be sine squared theta d theta. Okay, and then this integral here is pi over 2. So then we have 3 epsilon naught r cubed over 3, cancel, times 2 pi times pi over 2, cancel, and we get r cubed epsilon 0 times pi squared. Okay, and that's the result. Okay, so I gave you credit if you got to here and you didn't know that the integral of sine squared d theta from 0 to pi was pi over 2. That's okay. So anyway, but that's how you do that. And then problem number 5 was the boundary conditions. And so the boundary conditions are that we want the v to whatever our function is for the potential. It's got to be 0 when y equals 0, so anywhere along this bottom plane. So y equals 0, and then it's got to be 0 whenever y equals a. Okay, so that's your two conditions for that. Then you need it to be whatever this v is along that thing when x equals 0. It's got to be equal to that. And then as x goes to infinity, as you go this way, then you need your potential to go to 0, because it's going to die as you move away. That only charges on that wall, and as you go away from it, it's got to get weaker and weaker and weaker. Okay, for this one's a little bit easier. You need v to be 0 at y equals a, or y equals 0. So that's the top and bottom of this thing, and then you need it to be equal v0 at plus and minus b. I had a couple folks say that it needs to be equal to v0 between b and minus b, and that's actually what we're trying to figure out, is what the shape looks like in between minus b and b when we're just writing down the boundary conditions. Okay, and then those are the boundary conditions. All right, number C, what is the fourth Legendre polynomial with argument cosine theta? So there was a little bit of confusion. Some people interpreted this to be the Legendre polynomials go 0, 1, 2, 3. So some people put L equals 3 and some people put L equals 4. I took both of them. I intended it to be L equals 4, but that was, I should have said L equals 4, not the fourth. So that's me not being very clear. But then we use this, our generator function, the Rodriguez formula, to figure out what that is. So we have 1 over 2 to the 4th, 4 factorial, d cosine theta to the 4th of cosine squared theta minus 1 to the 4th power. And this cosine theta is equal to, this was actually what I was looking for. So if you had that, and even if you tried to go further than that, I give you credit for that. But that's basically what I wanted to see. And you could simplify this a little bit in like 1 over 384 or something if you wanted to, but that was basically, I was trying to give you some freebies there. Okay, then D, what is the approximate potential for the monopole? So for this one, I wanted you to just write this down and say that there's your monopole, there's your dipole, and there's your quadrupole, and then you could say that for the monopole, it goes like Q over R. For the dipole, it goes like 2Q over R squared and 3Q over R cubed, something like that. So just approximately using this and just kind of describing what this formula is. Okay, that's the exam. Bye.